that you can do there. And these other types of networks, you can set them up to do whatever you want to there. Okay? And so how you mix these two together, where, you know, there's good things with centralized, there's good things with decentralized. They each have their advantages and disadvantages. Some work in some places and some work in others. But what you need to make sure of is, what we're going towards, you want to have one device that works everywhere. You don't want a different device that works for each one of these systems. And now when I walk outside, I say, oh, my wireless LAN isn't working out here. Now I need to pull out my cell phone, whereas inside I needed to use my Wi-Fi phone or whatever there. You want one device to do it all. So you need these centralized, or you need these heterogeneous networks and heterogeneous devices. And just as one point was the fact that they just recently formed this IEEE standards committee that's looking on heterogeneous types of networks. Yes. So, any of you have any questions as I'm talking? Feel free to interrupt me at any time.
Do you really think that it can be distributed completely? Like it's network device-centric distributed mechanism is what you're talking about, right? Finally, you want to do everything in a distributed way.
Right, but you have to keep in mind that you may also be linking back to a network through a centralized network that you have no control over itself. So you really want to design a network where you have the ability to do some of the design yourself, but there's pieces of it that are there that can enhance the performance of the system, but you don't have any control over it. It's been fixed by the companies. And in addition, things such as cellular and WiMAX, if you come up with some great new idea, it's going to be a long, long time before that's ever implemented. Whereas if you come up with, as the company I was with before, Motia, and I'll be describing some of their stuff here as well, come up with some new idea for wireless LANs, you can implement that today. Okay? So again, we have a wide variety of different wireless systems that operate well in different types of environments. You might recognize this is one of the view graphs that used before there. I remember giving a talk, and Paul Henry was there, and he used the same view graph I did, and we couldn't figure out which one of us had actually, or who we stolen it from to get it in the first place. Yes. So anyways, here we're just showing peak data rate as a function of range. Data rates going up to 100 megabits per second. What everybody's working on right now are things that go up to a gigabit per second. And so I've been involved in some of that stuff for LTE for cell phones, and the latest 802.16m, which is trying to get a gigabit per second in WiMAX there. But anyways, you have all these different systems operating over different ranges and distances. Cellular that gives you large ranges, but generally lower type of data rates. And then Wi-Fi systems that will give you higher data rates, but generally over shorter types of distances there. So I was just trying to show you have a mixture of techniques, each having their advantages and disadvantages there. So as we saw, no single wireless system is going to be best in all cases there. And increasingly, multiple systems then are integrated into devices. We have Wi-Fi and RFID being integrated into cell phones, Wi-Fi, WiMAX, and cellular being put into laptops there. So to improve these systems, though, as I'll get into in the next view graph there, all these types of systems, whether it's Wi-Fi, RFID, WiMAX, cellular, all are looking to use multiple antennas. That is, smart antennas are being considered, implemented in the standards, and being implemented in each one of these systems there. So I'll just briefly go over smart antennas. Most of you probably know what we're talking about here, but I'll just hit some of the high points here. So smart antennas, we're just talking about a multi-element antenna array where the signals received at each antenna element are intelligently combined to improve performance. Reverse is done on transmit side. This will increase the signal range, suppress interfering signals, combat signal fading, and increase the overall capacity of these wireless systems. And although you can do it with a multi-beam type of system, the one that most people are implementing today is the adaptive antenna array, where you just have these multiple antenna elements. You're adjusting the weights to form an output signal that maximizes the performance, basically in terms of the signal to interference plus noise ratio of that output signal there. And basically the advantages of the adaptive array is the fact you can get it with M antenna elements you can get a gain increase in signal-to-noise ratio of a factor of m. You can also suppress up to m-1 interfering signals. And when you have multipath, you can also get an m-fold diversity gain. And of course, the big advantage of using MIMO, multiple input, multiple output techniques, where you use M transmit antennas to get an M-fold data rate increase in the same channel with the same total transmit power there. And so this is just showing the MIMO technique there, using multiple broadcast and receive antennas at, say, a laptop, a handset, or whatever, and the base station as well. And the key thing is that MIMO, I worked on this back in the early 80s, but people weren't interested in that, and they weren't even interested too much in the 90s as well. What's actually happened, of course, is that for single antenna, what you really want to do, since antennas and their RF chains cost money, you want to do the best you can with a single antenna, and as much signal processing as possible with the single antenna until you start approaching Shannon capacity. At that point, you have to say, how can I get a better performing type of system? The only way to do that in that case is to use these multiple antennas. And therefore, you can linearly grow the capacity of the system with the number of antennas that you use in the system. And of course, the interesting thing is, again, with M transmit, M receive, you can get M independent channels to increase the data rate M-fold. No increase in total transmit power, as long as the multipath is sufficient. And what's been shown is outdoors, the multipath is rich enough to get about a 10-fold increase in capacity, and indoors, about a 100-fold increase in capacity. So, but in practice, most people today are only looking at using 2 or 4 antennas, so we're away from what these limitations in terms of the ultimate capacity increase that MIMO can get to us there. We've got.
So what do you mean a 150-fold increase in theory indoors? I mean, are you suggesting 150 antenna pairs, or is it?
Right. So if you had a system indoors, and I could put as many antennas as I want to on my laptop, okay? If I put 50 antennas, I'll see the data rate go up by a factor of 50. If I put 150, I'll see it go up by 150. But if I put 200, it still only goes up by 150. Okay? Because the multipath is not rich enough indoors to go beyond 150.
But 150 is a lot of multipath. You think the indoors is that much multipath?
Yes. There have been a lot of measurements done and modeling done to show that that's how rich it is in typical indoor type of environment. And outdoor, the typical environment has about a 10-fold increase in capacity.
I would have thought the other way somehow.
That the multipath would be richer outdoors than indoors?
Well, I would do,
The walls, but you have more terrain outside.
Maybe you have a whole lot of money.
at least you lose almost one dimension, right?
Yeah, I suppose you're right.
Is that outdoor number urban or rural?
It really doesn't matter. It doesn't. I've given a range of 8 to 12, and whether rural will be closer to 8 and urban will be closer to 12. Okay. And when I was at AT&T, same time Larry was there, we had we easily showed you get a 4-fold increase no matter what type of environment you have there. So the point is that even though they're only putting 2 or 4 antennas, there's still a lot of room to grow and put a lot more antennas into these systems. And so when we talk about systems that are maybe 10 years out, which is what we're supposed to be looking at in research anyways, we're looking at perhaps having 10, 20, up to as many as 100 antennas in these systems in order to get these gigabit per second type of data rates and tens of gigabit per second type of data rates that people somehow seem to think that we will need in the future, although I'm not sure exactly what they would be used for there, but maybe we'll have video types of systems there. So with that, the one thing I want to start looking at how you actually implement these multiple antennas. And there's 2 ways to go about implementing a system with multiple antennas there. One way is to do it with analog or RF combining, and the other is digital combining. So, although I should actually have a diagram or something here. In analog combining, what you do is you take the signals at RF for example at 2.4 gigahertz, and you adjust the phase and amplitude of those signals at 2.4 gigahertz, and then combine them together to give you a single 2.4 gigahertz signal. And then you convert it down to baseband and run your A to D at that point. With digital beamforming, what you do is you take each individual stream, each antenna element, convert that signal down to baseband, and run it through an A to D there. So what are the advantages and disadvantages to doing it each way? Well, digital actually has better performance because you can do much more signal processing if all you have is all the digital signals there. On the other hand, analog actually has a big advantage there in the fact that digital requires M complete RF chains, including M, A to D, and D to A converters there, whereas the analog only requires one A to D and D to A for analog, plus the digital also has the substantial digital signal processing that goes along with it. What does that ultimately mean there? Well, what actually happens is that even though analog in general will perform poorer than digital, but because of the much lower cost here, you can actually have many more antennas and combine them in analog for the same price as what you could do for the combining for digital. So even though the performance for the same number of antennas is going to be poorer than digital, if you look at it on a cost and a power basis, you find that analog combining actually has much higher performance than what you get with digital, simply because you can do for the same cost and complexity, do more antennas with the analog system there. However, the one thing that digital does have that you, there are some techniques, but generally you can't do with analog, is when you talk about using MIMO, we just talked about the multiple spatial streams, you basically have to have a number of digital streams that's equal to the number of spatial streams, so you can separate them out digitally. Analog does not do a very good job of completely separating out the signals. It's best at increasing the signal-to-noise ratio. So what we've looked at and what we've been implementing is the use of RF combining that you actually need in these systems. So if we talk about a MIMO system that has two spatial streams, we're going to have a handset that has, say, 4 or 8 antennas on there. We're going to combine the signals from those 4 or 8 antennas down to 2 separate signals, and then convert those 2 signals down to baseband and do the A to D conversion there and do the digital signal processing after that. And that allows us then to have many more antennas and get the performance of a many more antenna type of system without the cost, complexity, and the power becoming prohibitive there. There's also as well many ways to actually implement these smart antenna algorithms. The main way, or what you need to be able to do in these types of systems, is you need to be able to identify the desired signal and distinguish it in some way from the interfering signal itself. Now, the standard way is to do what's called a non-blind technique, which is basically to take the received signal, demodulate it, look at the symbols there, and see if there's a particular training sequence on there. And then you can identify this is the desired signal if it has the training sequence, and say it's the interferer if it doesn't have that on there. But particularly if we want to do some signal processing at RF, we might want to do these blind type of algorithms. There's many types of blind algorithms, and actually in the jobs I've had over the last few years, we've been looking at each and every one of these, and they have their different advantages and disadvantages in different situations. The one I want to concentrate on here is one using maximum ratio combining, where you're trying to maximize the output power given a constraint on what these weights are. So if you say the sum of the squares of the weights is equal to 1, you want to adjust those weights to maximize the output power under that constraint, and that then will maximize any signal that's coming in here. It'll beamform on any signal that's coming in here and basically get you a maximum ratio combining type of gain, a factor of M in terms of antenna gain, as well as an M-fold diversity gain when you have these M receive antennas, by doing this blind type of algorithm there. But there's other techniques, and we've used those as well: constant modulus algorithm, power inversion algorithm, and power out of band type of algorithms to be able to blindly receive the signals there. Now, if what you look at is taking, let me just jump forward here. If what you look at is, one thing you can do with the blind beamforming is actually come up with what's called an applique, which Larry should be familiar with what we worked on at AT&T, and then actually at Motia we implemented that, and I left the box out in the car, but that's now a commercial product people can buy there. And basically what that does is it takes any received signal coming in and it adjusts, using the blind beamforming technique, it adjusts the weights in such a way to maximize the output signal-to-noise ratio for these antennas coming in there. Because it's a blind beamforming type of technique, it allows you to do a couple things. First of all, it'll work with any type of system, whether it's cellular, wireless LANs, WiMAX, any type of wireless signal that comes in will be maximized, or you'll get the smart antenna benefits for using this RF applique here. The second thing it allows you to do is, because it comes out at RF at this point here, you can actually take a standard wireless transceiver and now just remove the antenna and replace it with this device here that has, say, 4 antennas versus the single antenna that's there. Yes?
So can you elaborate what you mean by, or maybe you already covered this in the beginning of your talk, what exactly are you implying when you say blind? Are you saying there's a lack of training or pilot, or
there's a
blind beamforming?
Blind means it's not looking for a particular training sequence or any type. It doesn't require demodulation of the signal. Nowhere in here is the signal been demodulated. That is, it hasn't been brought down to baseband and look at what the data is that's on there. Because it's blind, it doesn't matter whether it's a cellular system or a wireless LAN signal that's coming in here.
But if you're doing it digitally, then you could use the information that's out there in terms of pilots and so on.
That's right, yes. But if you did that, and you build up a chip that did that, there's 2 issues you run into. The first one is it's now specific for that particular system. The second thing that comes in here, this technique here, because it's done in the analog, it's actually able to, on a packet-by-packet basis, calculate what the weights are. And it calculates those weights in a time period of less than a microsecond, at least for the chip that was developed here. And what that allows it then is a packet comes in, it immediately adapts the weights, and so as far as this wireless transceiver is concerned, it doesn't see any, it doesn't even know that the RF applique is on here, it just sees a stronger signal coming in. And then you use the same weights on the transmit side to just transmit back out again, you get the same gains in the other direction there. And so that allows you now to have something that very rapidly calculates the weights, which you couldn't do if you did the digital approach you're talking about. If you had to demodulate the signal and detect the data, by the time you did that, the signal would have already passed. Okay? And you don't want to store it because that would add additional delays in here as well.
And this is insensitive to which band? I mean, for instance, I see that you've listed cellular, various types of Wi-Fi and WiMAX.
Right.
So therefore you're saying these are sort of robust, I mean you can use the same sort of front end to do across different bands? Is that
right. As a matter of fact, what we did at Motia was we had a chip that operated anywhere from 700 megahertz up to 14 gigahertz. Okay? And that allowed you then to, generally there was some kind of control here to tell it which band to pick to beamform on that particular band. So if you tell it it's a cellular system at 900 megahertz, it's going to beamform on the 900 megahertz. If you tell it's a wireless LAN at 2.4 or 5 gigahertz, it'll do that as well. And we use this for mobile DBS, which is to receive satellite TV signals. That can be used in this case as well, because what we had actually implemented, and we tested this out and actually implemented it. I had some more pictures I can show you, but we implemented a flat array that goes into the roof of the vehicle, so you can watch HBO or whatever as you're driving around in your car. And of course, you don't want a little dish up on top of your car that's rotating around. And this was a flat antenna that fit into the roof of the car. And so with this IC, it allowed you to do that for under $500, and so you can watch satellite TV as you drive around. But it requires then electronic, because you can't mechanically steer the antenna, electronic combining, and that operated at 12 gigahertz there. Okay?
How robust is the antenna design across? I mean, is there loss of gain in some regions, or if you could optimize the antenna elements for 2.4, how much better would you do relative to a design that goes all the way from 700 to 14?
Right, and even when we made a chip that operated from 700 up to 12 or 14 gigahertz, there were different antennas that we used for each band.
So you
And
could
each-
switch antennas for each?
Yes, well, the applications were different as well. And for example, we used it for 802.11a and B and G, which operate either at 2.4 gigahertz or 5 gigahertz, and there were separate antennas at 5 gigahertz than at 2.4 gigahertz.
So we were talking to a car manufacturer before yesterday, and they want the same antenna for very wide band, so it's
Yes.
that as a possibility.
Right, and we were looking at, for ultra-wideband, I mean, this works in ultra-wideband as well. For ultra-wideband, you want something that covers, doesn't go from 700 to 10 gigahertz or whatever, but it covers a lot of those, the different bands there. But yeah, it's how you design the antennas. You can use like fractal antennas. There's all kinds of, and the other thing that we've been looking at is the use of active antennas, where you actually have MEMS and different types of devices in there where you electronically control what the pattern or the optimal frequency is. And the ability to do that in combination with a chip that covers that band now allows you to have a receiver, and this is what I'll be talking in the next view graph here, is if you want to talk about a multi-platform type of device, what you really want to do is, rather than having a different set of antennas and a different set of combining and processing for each band that you're operating in or each different type of system, you'd like to have something that's common to all of these and then just have the software be different. Because in general, you won't be operating your cellular, your Wi-Fi, and your WiMAX all at the same time. You would just be operating one at any given time, and so you just have one common piece that does all this.
Jack, before you go on, you said something about using the same weights on the transmit direction.
Yes.
Does that assume you're operating in time division duplex mode, or will it even work in cellular, which is...
Right, I'll get into that, and I like questions that lead to my next view graphs there. Okay. I'm not, gotta remember.
Prearranged?
What's that? Yes.
You guys didn't arrange this over lunch?
Unfortunately, Larry didn't finish.
Yes. So what we're trying to do is use these multiple antennas to increase. I guess it's not the next. A couple of view graphs, anyways. There. Okay. So we're trying to increase the performance by using smart antennas of all these systems to increase the range as well as their data rates. And so let's look at the example here I was talking about for wireless LANs, which are time division duplex operation. They use the same frequency to receive as they do to transmit. And that allows you to do, as we just mentioned, use the same weights for transmission as you have on reception. And now you get the same gain on the transmit side that you get on the receive side there. And that allows you to, for example, put this smart antenna just at the access point and get performance improvements in both directions, or just put it on a laptop or your wireless device and get improvement in performance in both directions there. And this shows what kind of gains that we actually achieved by using this commercially available chip there. Any question? No? Okay. And what we got in this case, this is 4 antennas with a blind beamforming chip that we were talking about before. And the gain over a single antenna type of system, with it on one side that is just doing it for receive and transmit at either the access point or on the client device itself. We get about a 13 dB gain with these 4 antennas, and that'll give you about a 2 to 3-fold range increase. If you put it on both sides, even though each side is operating independent of what the other side is, you actually get about an 18 dB gain there. And this gives you about a 3 to 4 times range increase. Now, yes?
So these 4 antennas you're talking about are at the access point?
No, they could be at either side. So if I put it on the access point, I'll see 13 dB gain on the uplink as well as on the downlink. If I put it on the client side, I'll also see a 13 dB gain on the uplink and downlink. Okay? If I put it on both sides, I don't get 26 dB, I only get 18. There's 2 reasons for that. Right. First of all, if it's on both sides, I'm not jointly optimizing them. They're each operating independently. But the big difference is the fact that this 13 dB, 6 dB is the array gain, and 7 dB is the diversity gain. But once you get that diversity gain on one side, you can't get another 7 dB diversity gain on the other side. You only get a few more dB there. So the results that were measured then was to go to 13 dB with the adaptive array on one side and 18 dB if you put it on both sides there.
These are measurement results?
Yes.
How did you create a Rayleigh fitting channel?
How do you what?
How did you create a Rayleigh fitting channel? I think this is only for Rayleigh, right? I mean, even if you have a line
That's
of sight,
right.
your gains will come down to. Did you have line of sight channel also?
We have line of sight there, but you still have some multipath fading that would reduce. That makes correlation. The fading have correlation, and then so the gains start to reduce.
How much is the reduction? How much is the reduction for when you have line of sight?
Oh, it varies on how much it's Ricean rather than Rayleigh. And actually, and although that will only generally the cases that we studied, it only reduced it by a couple dB. A big killer for this is the fact, let me just describe this kind of stepping back here. The blind beamforming that operates at RF calculates one weight over the entire band. If you have frequency selective fading, that weight is not the optimum weight across that entire band. You will see the performance degrade because you didn't do it on a tone by tone, or you didn't have an equalizer in there to compensate for that. So with substantial delay spread, the gains come down several dB again. But one thing that is happening here, whether this is with B, we also did the same types of gains with G. B is a single carrier system. G is an OFDM system. Now, obviously, in OFDM, you'd like to have a different weight for each one of those tones there. You can't do that at RF unless you really make it really complicated, okay? And we didn't do that. But even though you'd say, well, when there's delay spread, the weights at one end would be completely different than the other end of the bandwidth that you're operating at. But what actually happens is, even in an OFDM system, they're still doing some coding and some processing at the receiver that was capable of handling the delay spread type of situations. So even though the weights are no longer optimum, there's still delay spread compensation being done at the receiver. At B, there may be some equalization being done. In G, there's some coding across the tones. We looked at WiMAX systems and similar types of processing going on there that actually mitigates the problems that's going on. And actually what we found in, this is for Wi-Fi, but we did this for WiMAX systems, we actually got an improvement in performance with delay spread. And you'd say, how can that possibly, or for certain points with delay spread, you say, how can that possibly happen? It should degrade. Well, what actually happens is the receiver, if it just had one antenna and there was delay spread, is trying to compensate for that delay spread that's going on there, and there is some degradation in performance when it tries to compensate for that. When we do our beamforming, we're getting not only a strong gain, we're actually beamforming basically on one of the strong rays that are coming in there. And because of that, we're actually changing the delay spread profile that makes it easier for the receiver to compensate for that delay spread. And the overall effect is that the gains in some cases become larger for particular delay spreads than what we're showing here. And in WiMAX, as an example, these gains were going up to 15 and 16 dB over a single antenna system. And the delay spread was not, I mean, obviously the performance versus no delay spread gets worse, but for a given delay spread, the gains that we would get with these blind beamforming techniques is actually greater than what we get in a non-delay spread or frequency flat fading environment there. Okay? So, kind of stepped ahead here, but here's WiMAX. And a key issue with WiMAX systems, and this is what we had worked on there, was for 802.16 versus 802.16e, you're talking about the ability to take a system that originally had an antenna outside a building, communicating back to the base station, and you want to make it so it's truly portable. So you want to be able to do it inside a building, as well as put it on the laptop, for example, Well, once you put it on the laptop, you no longer can use a directional antenna. You have to make it adaptive, and that's what we wanted to do here. As well as you have to overcome the building penetration loss, which is on the order of about 10 dB. As we showed before, 4 antennas gives you that 10 dB type of improvement. So with these multiple antennas, and the technique that we're talking about, we were able to get the same performance for a WiMAX system on a laptop using a little PCMCIA card inside a house as you got putting these pizza boxes on the outside of the house there. Okay?
Would you say the equivalent gain is 13 minus 6 because most of these would tend to be sectorized kind of antenna? If you take a typical existing base station, it would have sectorized.
Well, I was talking about putting the smart antenna IC on the client device, not on the base station. As a matter of fact, in WiMAX, the real problem you have there at the base station is that most of these systems, at least the ones being deployed now, are OFDM-A. They use different tones come from different users, and you can't use a beamforming device that right across the entire band. It just it doesn't work at all. Plus, of course, for the company I was with, it made sense because there's a lot more client devices out there than there are base stations. Somebody else can worry about the base stations. We're making a chip that we want to sell millions of. Forget about the base station. We're working with Intel on this to get them implemented into laptops there. And that's what Intel is doing there. Okay. Now, in cellular systems, this gets to your question, Larry, is that cellular systems are, rather than being TDD, or FDD. They use a different frequency to receive than they do to transmit. You calculate the weights on reception. You can't use those same weights on the transmit side. And so we looked at a variety of techniques that we could actually use in cellular systems to figure out what to do on the transmit side. And people have looked at this in the past there, and I'm just going to kind of go over the things there. But the 4 antennas basically provide about a 6 dB increase in cellular systems, both on the receive side as well as on the transmit side. Now, how do you get these types of gains on the transmit side? Well, if we look at the different types of systems, we have a GSM system, Cdma system, and this DVB-H or TV type systems. Of course, the easiest one to handle is a DVB-H type of system because that's downlink only, so you don't care what you're doing. You don't have to do any transmit at all.
So how do they do video on demand on these events? A relevant question for the talk, but can you do any kind of video on demand on DVB systems?
They don't have those out there right now, as far as I know. But the reverse channel to do it's a low, right? So you don't really care whether or not you get that. And then you can use GSM or CDMA to do the reverse link. And the second easiest thing to do is a CDMA system. And this is what Qualcomm and Magnolia Broadband, if you're familiar with those companies, are doing there. You simply use the power control bits that are available in the CDMA system to adjust the transmit antenna pattern. And basically what you're doing is I don't know if you're familiar with that or not, but you're basically changing the transmit weights in a kind of gradient search type of method where you're looking at the power control bits coming back. You adjust the phase of one antenna one way, and if you see that the power control bits say, oh, I've got more power now, you know you went in the right direction. You keep going there till it says that the power is being reduced, and then you know to go back. And so that makes it very easy to get gains on the transmit side. And in GSM systems, what you can actually do is use the receive weights averaged in some way over the fading. This won't give you any diversity gain, but can give you the array gain there. Yes?
The power control bits are around 800 hertz or something, so is it enough frequency for adaptively changing the weights?
That's right. If it wasn't, it couldn't track the fading that was going on anyways. Right? I mean, the power control is trying to track the Rayleigh fading that's going on. And that's indeed what you're trying to do in the systems when you're transmitting. You want the transmit diversity or the gain. You need to be able to be tracking the fading that's going on. And those bits are fast enough in order to track the Rayleigh fading. Therefore, they're fast enough to adjust the weights to get very close. And actually, the interesting thing on the transmit side, and it's the receive side as well, if you're just trying to get signal gained, you don't have to be very accurate with those weights. If you wanted to suppress something 30 dB, you'd need extremely accurate weights. But what we did for these techniques here, the weight accuracy only had to be within a few dB, and you could have a 30-degree angle error in the phase itself, and that would only lead to a 1 dB degradation. So you've already started with 13 dB. You can tolerate a 30-degree phase error before that actually degrades the 13 down to 12. So these are not serious issues there. And as a matter of fact, because of that lack of any requirements, we don't even have to do calibration on the transmit side. Normally, if you want to transmit out of the same antennas that you received with, it's going through different circuitry. You need to calibrate that circuitry in order to get the same performance in both directions. But if you're only interested in dB accuracy and 30-degree phase shifts, and you're doing this all as we were doing on a single chip, there's no calibration issue at all there. That you can put it in any device and be guaranteed it's going to work fine every time then. Okay? Now, the thing that Eigen Technologies has been focusing on has been in RFIDs, and their adaptive arrays have been looked at, and I'll discuss what the work we're doing here on both readers as well as tags. If you're familiar with RFIDs, and I guess you're doing some work on RFIDs here, so don't have to go into too much detail here, but you have both active as well as passive tags. We've been working for the government here, the Army specifically, Department of Defense. They have active tags at 433 megahertz with a read range of about 300 feet, and passive tags at 900 megahertz that have a read range on the order of about 9 feet there. Now, you can use adaptive arrays on the readers, for example, to scan the beam on the transmit side, then the adaptive array on the receive side as well. And the tag can actually use adaptive arrays to receive and then use the same weights to transmit at. And I'll be discussing how we actually go about doing that in just a minute there. But just to look at the problem that the Army the Department of Defense was dealing with here. As I mentioned before, the active tags have a read range of 300 feet. And you'd say, okay, well, then I'm pretty secure, because if somebody's within 300 feet, I probably know where they're at. But that's with an omnidirectional antenna. And so you can just go through some calculations and figure out what you can do if you have high gain antennas. And with the numbers I'm showing here, we're actually able to show that you could have a satellite, an airplane, you could be standing offshore. With a high enough gain antenna, you can actually read exactly what's on all these devices there. And as I was mentioning at lunchtime, we're working on security for these types of things, because right now what the military has deployed, and this shows it going, I guess this is the San Francisco, but whether it's going to the Persian Gulf or wherever, the tags that they've deployed right now have no security on them whatsoever, so anybody can read what's out there. So the contract we have is to do encryption and things, and do it in a power efficient type of manner there. And so with the current system, though, the way it is, just about any adversary can be able to figure out what's going on those types of systems there. So arrays can greatly extend the range there. The other thing we've been working on with another university has to do with adaptive arrays for your RFID tags. Now, RFID tags are very small devices. They're on these little tiny chips. So the tags can be very small devices, single chip type devices. And then you say, well, how do you do multiple antennas on a little tiny chip there? For example, at 900 megahertz, if I did the calculations right, half wavelength spacing 6 inches. You can't have a little tag and then have the antenna spaced 6 inches apart there. Okay? So the solution that we've been looking at and working with another university on this is the use of carbon nanotube antennas. Carbon nanotubes, if you go through the calculations, you can show that the wave velocity is about 1 to 2% of what it is in free space, which means when you build your little antenna, the optimum size of that antenna is only about 1 to 2% of what it would be in free space there. So rather than having 6-inch spacing, you actually only need about 1.7 millimeter half-wave spacing. So you can put a lot of these antennas in a very, very small area. And I guess the other way to look at it is in the same area as a standard metal antenna, you can put 10,000 antennas in there. And of course, if you now put the blind beamforming on top of that, you can combine it all together there, and you see there's some potential. There's some issues such as antenna efficiency. This is I got to make sure that this is a research topic. I gave this presentation a couple weeks ago to the Antenna Propagation Society out in Long Island, and they started ripping me apart because there's some serious issues that need to be considered here yet. And I presented it, here's the solution, and that didn't go over well. But there's a lot of research that still needs to be done, but the potential is there. And one of the things I always find is to just exclude using adaptive arrays on RFID tags because they're so small. There are potential solutions to get around that. How you actually do it, how well that works, is still something that needs to be worked out. Yes?
Jack, did you put in that last line after you got attacked by the A&P Society?
No, this part was in here.
Okay.
Actually, I didn't change it because when I presented it there, I had solution. And the next time I gave this talk later on in another place there, I put potential solution, and that deflected a lot of the questions there. And I thought about that this morning and putting potential in here, but I think it's a friendlier crowd than the Antenna Propagation Society, I think.
This is a very friendly question. I don't understand what you put there, right? So the way I sort of understood it is that essentially you have a carrier frequency that you transmit at, right, corresponding to you get a wavelength. And if you look at sort of a correlation model that's sort of roughly like a Bessel function, then you get like half wavelength is essentially the spacing at which you get uncorrelated.
Right, yes.
So now when you say you have carbon nanotube antennas, this is sort of really physically the material of the antenna itself.
Right.
But how does this sort of relate to what happened to my propagation and all the signals that came in? When you say I have 10,000 antennas and it's only like about, the half wavelength is only about 1.7 millimeters.
Right.
But it goes much slower.
Translation between
It's
this
like
and that.
translating the RF into the acoustic waves, not really acoustic, right?
At the speed of what acoustic is, similar to what that would be. Now, indeed, you're not going to see across the aperture changes of the phase related to the fading that's going on.
Right.
So you cannot expect that you would get much multipath fading mitigation.
Okay,
But what we're trying to do with the tags is to also provide an antenna array gain. In particular, since the tags are limited in how much power they have available in order to transmit, you'd like to focus that energy back towards where you got it from. You want to increase the range, so you want to have an array gain on that device there somehow. And this offers the potential for getting some kind of array gain with these multiple antennas. Of course, you're still limited by the fact that the chip has a small tag size there. And that, one thing, it leads to a very low antenna efficiency. But you'd have a low antenna efficiency anyways if you tried to put a metallized antenna or metal antenna onto the chip itself there. Okay? But so these are certainly research topic. No one has actually built and demonstrated a carbon nanotube antenna. That's the starting point. And I'm going beyond that and saying you're going to do arrays of these. So I'm talking about using arrays of things that no one's even demonstrated a single one yet. They've only had papers that discuss this theoretically. But the military, for example, is very much interested in these types of things. And the idea is if you can do a carbon nanotube antenna, they can be manufactured at the same time that the chip itself is made. So the same IC manufacturing processes can actually be made to implant the antennas onto the chip itself. Okay? So kind of led up to this there, but basically what you're interested in, you have multi-platform devices. We've shown smart antennas work very well to improve the performance, and that all future systems, as far as I'm concerned, or believe, all future systems are going to have multiple antennas on there. But obviously you cannot have multiple antennas for each one of these types of systems if you're going to have a multi-platform device. Before you know it, you talk about putting 100 antennas on your laptop, but if I now want to have it Wi-Fi, WiMAX, cellular, I'm going to have 100 antennas for each one of those, and that's certainly not going to work very well that way. You can envision putting a couple antennas on here. Companies are considering putting 4 antennas by 2010. And one of the companies that I'm working with is Mobicom. And I wanted to show this cell phone that will be out in another couple months here, just to show the small physical size of this thing here. And this is a fully functional cell phone. It only has 5 buttons on there, so what you actually do to program this thing, and I've done this for my phone here, but as I find it doesn't work in this building, so I can't demonstrate it here anyways. You just go on the web to a certain page, and it sends a signal to the cell phone and programs these buttons to whatever you want it as numbers to call. Or if somebody calls in and you want to call them back, you just press the button, and it gets redials the number back out there. But the point here is that the phones are becoming very, very small, very, very tiny. What you want on this company also makes the Firefly phones, and the next one to come out a couple months from now will be same size phone, but will have a full display that covers the entire front of the phone there. So these are becoming very small, and it's just not going to be cellular. You want this thing to have Wi-Fi in there. If you follow the, as I said, this company also works on these Firefly phones, and those phones themselves actually have GPS in them, so you can track. And talking about before that you give a little phone like this to your kid, and it's kind of nice because it's only got 4 buttons on there, so it's call mom, grandpa, and a couple of the friends, and you give it to your child or whatever, and because it has GPS, you go on the web and you know exactly where your kid is at any time, and you don't have to worry about them dialing numbers they shouldn't be dialing when they're on the phone there, and you put a screen. But the point is that they're becoming smaller and smaller. We want to put more and more platforms, more systems onto these phones. How do you do that and still fit it all into this phone if you had to have multiple antennas for each one? Yes? That one only has 1. Okay. No, 16, yes. We're looking at ways to put these multiple antennas. So you want to use the same front end, use this blind beamforming IC basically approach to do this. And that way you can add more platforms at minimal cost and add more antennas to each system at minimal cost. And so I'm on this standard JEDIC committee, which what we just came out with is a standard interface. Standard interface between the RF IC and the baseband MAC. And what this allows companies to do then is come up with a standard front end that now will interface to anybody's 11N, whatever, Wi-Fi, cellular, RFID, GPS, whatever they have in there, that type of system there. And we did a serial interface, and the one we're working on right now is a parallel interface standard that goes with this. And so with that standard now, you can buy the RFIC from me and buy your baseband or whatever from Qualcomm or whatever company Broadcom or whatever company you want to work with there. Okay? So, I don't know how much, let's see, what am I doing on time here? I can talk forever, but so I just...
Start at 1:50.
What's that?
Another 10 for 20
minutes. No, 10 minutes? Okay. I just wanted to mention the work you've been doing on smart antennas and ad hoc networks there. Okay? So I probably don't have to go into what ad hoc networks are, why they're good, their advantages. But we look at what happens if you start putting smart antennas on there. So you're not only just having cooperative diversity, as an example, between the multiple nodes with single antennas, you want to actually incorporate these smart antennas into the systems. Now, most papers have been written on using directional antennas, but there have been a few on using adaptive antenna arrays, and so that's the type of work they've been focusing on there. And the key thing that this is trying to state is that even though some people think that smart antennas are a physical layer technique and that ad hoc networks is a MAC layer technique, you can't just throw in the physical layer and do the MAC layer independently. It's not going to work very well. And we've been really dealing with a lot of these problems with the standards committees, because I'm involved in the 802.11 committees. There's 802.11n, which is trying to get much higher data rates using these MIMO techniques. And there's 802.11s, which is coming up with how you do mesh networking. Now, I go to the 11s meetings, and I say, oh, you're going to have to use these mesh networks with 11n. The problem is they say, oh, we would like 11n to be considered as a black box, that we can take our mesh network with single antennas, and if we put 11n in there, we're going to have exactly the same performance. Everything's going to be exactly the same, except the data rate's going to be a factor of 10 times higher. Okay? And, you know, I gave them several talks showing that that was not going to be the case, but they dismissed that. Because actually the only thing they could consider, even what a smart antenna was, which is how it's envisioned here, which is just a narrow directional beam. And all that messes them up, because how do you do a narrow beam in a ad hoc network where you don't know where the node is, or now you have to put in the beam pattern as to what's going in here? So he said, no, you want an adaptive array, and they still have substantial problems they're going to run into there. But I just want to mention some of the problems with smart antennas. One has to do, and these really haven't even been completely worked out there. One's the association problem. You have an access point here, an access point here, a client here. It needs to associate with one of those two access points. It generally does so by looking at the beacon and seeing which access point gives you the strongest beacon. The problem with that is, if this access point uses a smart antenna and this one uses an omnidirectional antenna, you're going to associate to the wrong one in many cases there. And the problem gets even worse when you start moving around, and pretty soon you can find with these smart antennas you're associated completely with the wrong thing. And it's even worse. This gets into the 11n issue of what they have there. For example, at 2.4 gigahertz, you have 3 channels. So you could have A, B, C, and D as the nodes. There's only 3 channels available, so A can talk to B on C1, B to D on C2, B to C on C3. Everything works fine. Now you come along and say, I want to put 11n in here. I'm not going to put it in every node. I just want to put it between B and D, get a nice high data rate going in between here. One of the things, and they're going through the balloting process right now, they have very poor techniques to figure out what to do when you have mixed mode type of systems. Some that have 11 ABG and some that have 11N in there. And one problem that really can occur is they do channel bonding where they actually use 2 channels at a time. And if this link here does channel bonding, basically C1 and C3 can't operate. And this is exactly the problem that one company, I knew Greg Raleigh started a company called Ergo Networks. I don't know if you're familiar with that. It was just recently bought by Qualcomm. Their most recent product that came out was an absolute disaster in terms of how it worked with others, because it would go on there, it would grab, actually its 2 channels overlapped all 3 channels there, and because of the fact that it did interference suppression, it never even saw that there were other users out there. So you put that box in there, and hey, you got really high data rates on your box, everything else crashes. And the current 11N solution to this problem, I put quotes around the solution, is for the box to look and see if there's any other users out there that are using, that are ABG and not using MIMO. And if they see there are, they don't transmit for 30 minutes. Okay? And if there aren't, they start transmitting, and every minute or so they'll check to see if there's something else out there. Which, wait a minute here, that means I'm going to sit there, and if I happen to grab the channel and somebody else wants to transmit, they're not going to be able to get on for 30 minutes or so to find what's going on. And by that time, you've gone away, and so when he checks the next time, 30 minutes from there, there's no other users there. I can continue to use it. So,
What's channel bonding?
What's that?
What is channel
Oh, channel bonding is where to double the data rate, rather than just using channel C2, you use channel C2 and C3. So you use 2 channels that are adjacent to each other to basically double the data rate.
40 megahertz.
40 megahertz rather than 20 megahertz, yes.
So so when they do that, right, how much of the gain is coming from the multiple antennas and how much is coming from sort of the doubling of bandwidth?
Okay, I can go through all these calculations because if you talk about 802.11 A and G, it has a peak data rate of 54 megabits per second. The actual throughput is 18. They want to get that up to, and they have systems that operate at 500 megabits per second, okay? So you say, how do you go from 18 to 500 megahertz, okay? There's a couple things. You increase the efficiency of the MAC, and that will get you up, I guess I can't remember exact numbers for the efficiency.
That's 70%.
What's that?
70%.
Right, and so that'll get you up to maybe 40 megabits per second. And then you want to do MIMO with a factor of 4, so that'll get you up to 160. And then you want to do channel bonding, which will double it on top of that, and that'll get you up to 320. And then they have some other tricks that they play to get you up to. And the other thing they do is when you do channel bonding, ordinarily there's unused carriers in the middle. They make it so the two carriers don't.
64 out of 52, right?
Right.
52.
So you go through all those calculations, and indeed it goes from 18 up to 500 megabits per second.
And you have one big client, and then it goes down to 11 megabits.
Yeah, but
That's right.
The point of using
good.
MIMO is to not use more bandwidth. So, I mean, why channel bonding? I mean, I'm missing something.
The whole
You
idea.
know how to do MIMO very well yet, probably. You know.
And the other thing is, and we found this out so many times in the products we produced, people look at the box, and all they look at is what's the peak data rate that you operate at. They don't care whether, and the first pre-11N chips that came out gave you the high data rate 5 feet away from the access point, okay? Totally useless, but you can still put on the box that you have these, 100 megabit per second, yeah. And, what's that?
People don't really need 400, 500 horsepower cars, but they're still, that's still a selling point.
Right. They just look at that number. Can you put that number on the box? And as a matter of fact, what they're doing in 11N right now is 11N meant MIMO, okay, with multiple antennas, multiple spatial streams. Well, the handset manufacturers, in particular the people that make this handset here, said, we can't put 2 antennas on our system, yet we want to say that our cell phone uses 11N. How do we get around that? Oh, they changed the rule now. If you're a client device, you only need to use 1 antenna. Okay? Now you only get, you'll get 50 megabits per second, but now on the box you can put that you have 11N.
500 megabits, up to 500 megabits. Right?
Yes, it always says up to. Right. Okay, but there are solutions to this problem.
But does
Yes.
it figure out that if the other user has only 1 antenna, you can do diversity combining instead of, say, rate? Or even you cannot get multiplexing gains anymore on your...
But why even talk about that? I mean,
They
you
don't
have
have your
802.11b client, you forget about 10. It's not going to happen. When you lose every possible advantage, even bonding, you can't do even bonding. So right there, it's half of your rate is gone. Even if you don't have mine.
So in fact, I think the only use you can put the multiple antennas is to do some kind of beamforming. What you can do. You can get some gains from that.
Yes, you can do
That's what you do.
as long as
Right?
you know.
I mean, people who are claiming they're doing MIMO, nobody's doing MIMO.
But the other thing they did, which was to me was ridiculous, the MIMO systems gives you these multiple antennas, which should give you an increase in range. I was talking about 4 antennas being able to double the range. What did they do in these systems? They only wanted to get higher data rates at range. They did not want to increase the range. The range is based upon how far away you can associate. For association, you need to transmit an omnidirectional pattern. So even though you have the MIMO that's going to totally mess it up in terms of data rate, you'd say, at least I can extend the range. You can't. They didn't implement it to extend the range. The range will be the same.
That's an issue, right? Because
CSMA,
you screw up your carrier sense.
Exactly, your carrier
Because
sense
what
is going to
happens
go away
now,
if you're
I'm
beamformed.
alert to so many signals, I keep hearing stuff that normally would not bother
No,
me.
but even if the access point beamforms on say on beacon,
Yeah.
you will lose carrier sense
Yeah,
of all the
absolutely.
guys who are outside of the main beam.
Yeah.
So what do you do
Disaster,
there?
actually.
So that's it's a major problem. MAC has to be completely removed.
And you understand that if you go to these standards meetings, 11N, we'd have over 400 people sitting in there. You try to come to consensus as to what you do with 400 people. And this is just on the fly, okay? And you just throw MAC in, it's just...
We
simulation results.
Right, no one has done any computer simulations.
It's kind of interesting because I've been in different standards and this type happens a lot, but
Mhm.
MPEG was pretty good because they had a requirement that you have to bring a bit stream and give it to 5 other people who will check independently, and the whole standards meeting would start with a series of demos.
Right.
Then I think if we could do the same for
They originally set it up and they had functional requirements and usage scenarios. And they had so many different usage scenarios and so many different functional requirements. No one even compared anything together there.
But I have a rule of thumb that if a standard has more than 100 attendees, it collapses in quality. Like IP is an example. IP before 1998 versus after, there's a huge change because they got all these orthogonal standards which don't work with each other.
Uh-huh.
You know, QoS doesn't work with multicast. Same thing. So I think you're guaranteed to fail after that.
But in general, it's not how many people are at the meetings, it's how many companies are there. Qualcomm, for example, will have 20 or 30 people there, and I always complained to them that it looked like they all had strings tied together, because you'd see one hand go up, and 10, 20 hands would go up simultaneously there. And when I was at the standards meeting the one time, there were 400 people in the audience. They all have pre-meetings beforehand to determine how to vote. And that particular day, they got beyond what the agenda was going to be. And the next vote was 1 to 2. I voted one way and 2 people voted the other way, because even though there were 400 people in the audience, they hadn't been told ahead of time how to vote, so they didn't vote. And at that point, the chairman said, if only 3 people are voting on each measure, we're going to stop here. Yes?
I would also add, MPEG eventually decayed. Once it no longer became a bitstream society, once they started trying to do computer science things on top of it, that was it was over.
That was overreaching. Which is end is pretty much in that category. Because the Mac never worked, and if you think about it, 802.11 is mainly a Mac standard. The rest of it happened to be radios which have been around, and you choose one or more, but the Mac wouldn't work.
Right, and to get a consensus, to get people to vote, you have to include everybody's ideas in there. So 11N at one point had over 1,000 optional modes that you could use in there. Okay? It's just...
So talking about carrier sense, right? Then you could use it for these very dense networks where you could allocate time and bandwidth to people. Then you can do very well with money.
How? Carrier sense, I mean, if I don't see you.
What carrier?
You have the hidden node problem.
Allocate everybody a fixed slot.
That's
then
not,
it's
that's
How?
not,
That's
that's
not
not
carrier,
either.
that's not...
Yeah, no.
Some other
CSMA,
Mac.
you know.
Sure, you can design a new Mac. Sure.
Yeah, if you change the Mac, you can, beautiful.
You
no
have
problem.
to. If you really want all this to work, you need to design a
But
new
with
Mac.
CSMA,
Right, but that's not what
CA,
you're trying
forget
to
it.
do.
Yeah, you would anyway have to have an omni-channel to do your Mac.
To announce
Right.
things, right?
Right.
I mean, there is no... Yeah.
And so you can start and develop another standard to do that. 802.11 is now, there's A, B, G, N. Now they're up to 802.11y. So there's all kinds of different things you can do, each one starting their own standard to do that. Each one of them is having thousands of different optional modes and trying to get things to go. And another one of the things I like at the standards meeting is because you eventually want everybody in there to vote on whatever your proposal is and agree. When somebody goes up and gives a talk, if I said something wrong, you'll criticize and say it's wrong. I've seen the most erroneous talks being given there. No one says anything, and everybody claps afterwards. And you even walk up to the person after, very good talk, very nice. Because if you say, stand up in front of the crowd, this is wrong, you made this mistake here, and they're obvious mistakes that they wouldn't vote for your proposal the next time. Okay, so I just put this in the end. So we're looking at some joint multidisciplinary research along with standards development, antenna array design, looking at compact antennas, and looking at reconfigurable, both in frequency, bandwidth, pattern, and polarization types of antennas, along with cross-layer optimization, doing, as we were mentioning before, spatial stream diversity, cooperative diversity, dynamic spectral allocation, and between distributed and centralized radio resource usage optimization, a combination of those together. I mean, that'll keep me busy for another few years anyways there. Okay? So I think that pretty much covers it there. Smart